Welcome, and we are going to perform electrical signature analysis diagnostics on two submersible pumps. Two pumps, not submersibles. Be horizontal pumps as shown here and here and here. Give that a few seconds to show you what the pump systems look like. First one we're going to do is the larger pump stator, and that one is this one here, and that is across a line. And in fact, what we did with this one is let's pull up the nameplate, put that here so you can see the machine here, and this 500 horsepower, 890 RPM. You notice a little cheater pops up that tells you what each of these are. 4160, 64 nameplate amps. From the database down here, we got 76 and 96, 76 rotor bars and 96 stator slots. We do know the blade count is 6 on this split case pump, and then the bearings are 6320 bearings. They're not ZZ, they're actually oil bearings, so they have no shields on them. Over here, I can put other information directly related to the machine, but not going to worry about that. So, in any case, we have the nameplate here. That's already in. We're at 60 hertz. We are running across the line. I've selected, these are the options I have for different types of alarms and calculations. I have selected induction machine. On the other one, we will select VFD. Now, we did take current only, as shown here, which we can take a look at. Now, the data was taken off the back of a multi-lin. Those are the multipliers for the CT ratios. And then here, just for the sake of ease, I want to take a look at a couple of things. So I can change the minimum dB level if I wish. I'll do that a little later, and some other stuff, including the type of waterfall or what type of plot. I am here taking it as a flat top versus Hanning, which sharpens some of my peaks. And then here's my zooms and a few other things. These are the channels that we took, and then I can display. So anything that's highlighted here I can turn on. So just for fun, let's take a look and make it a little overcrowded. There we go. So let's go ahead and get rid of some of this because we didn't take voltage. I could go and just turn it off. Also do this. I do have the ability to do current or voltage demod as well. That becomes important when I am analyzing things like generators and so on. So this is my information here, and then here is my high frequency data set in current. Okay, so that are all three phases together. I can shorten this up, which will also change my resolution down here. To take a look and see what the waveform looks like. You'll notice that it's not as sharp down below. If I have a spot where something shuts off and I want to analyze around it, or just want to analyze that area in different loading scenarios, I can highlight that and it'll continue to change what I'm looking at down here. And then I can step backwards. Okay, so when I come here, I'm taking a look at this. The noise floor is just down below, but I'm not worried about anything really too much down at that level. Stuff I'm going to look at here includes blade frequencies, such as this one right here. Let's go ahead and set up the power harmonics, because anything that is a line harmonic, so it'll be green or red, I usually ignore. Everything else I can analyze. So I do have something going on with the blade. I can also take a look at things like interturn shorts. So not really. There's nothing going on there. This is a line frequency. This is the blade, of course, and I don't really have anything on this side. So the windings doesn't have any interturn stress. Stator mechanical, let's go ahead and zoom this back out. And this is the mechanical area. Again, I can zoom in and take a look. Stator mechanical, such as this. So I have some movement of the coils. So this would be coil movement, stator movement, something having to do with the stators. Could be on a large machine missing wedges, things like that. But this is usually movement related to the coil. With the age of these machines and their general condition, it is most likely movement of the coils in the slots. Let's go back and then let's take a look at things like static eccentricity, which would be the rotor sitting off to one side. Don't have any significant values of that. And dynamic eccentricity. Now, how do I calculate these? Well, I use the rotor bars and stator slots. So if I'm looking at, let's go back here, this here, where I actually have a mechanical issue going on of some type, you'll notice that these are 120 apart. So this is 1374, so the next one should be about 1494. And there it is, 1495 for that peak. So close enough with the resolution. So those are sidebands. So I add them together, divide by 2, which would give me a peak somewhere here in the middle. And I can divide that by the running speed, and that gives me the number of stator slots. So if I want to go the other direction, I would take stator slots 96 times the RPM plus and minus 60 hertz, and that would give me that. For the rotor bar related stuff, so static eccentricity, I would do the number of rotor bars, which in this case is 76, times the running speed, then plus and minus 60, plus and minus 120, plus and minus 180. Now I need to see at least 3 peaks, especially these two, showing up in order to say that it's dynamic or static eccentricity. Now dynamic eccentricity will be side bands of running speed of these bands. So if I come in and I hit dynamic eccentricity, you can see that I now have a shorter thing. These are running speed side bands around those. Sometimes you'll get dynamic eccentricity, often you'll get this. This is the rotor or magnetic field orbiting inside the stator. Bearing damage. So let's take a look and see if we have anything going on with the bearings. I've highlighted already, so we'll go back here. Let's pull this up. This is the calculator. So in this calculator, it's telling me I have unidentified peaks. So everything else, of course, I turned everything off, so it looks okay. This is the actual running current. This is the percentage of motor load and estimated efficiency. I can switch this over to horsepower if I want, but for this it's no use. We'll see that in the next one. This is the actual running speed as selected by the software. This is my pole pass frequency, and I will have any of my total harmonic distortion listed here. That's the line frequency that it detected. So in my bearing, I do not see anything here, so that is in pretty good shape. Phasers will show my harmonics, in this case current. You can also look at the actual values. And extras will give me torque, and also this is these are points that are trended in the software. So if I have trending going on, I'll have those. So let's come back here to results. Now what I can also do is this. If I right click on here and I select running speed and pole pass frequency, let's see if that changes. Nope, it's still there. Now I don't see anything with the stator bearings, so that means that the bearings in the pump are probably an issue. We did detect that and confirm it with vibration. So let's take a look at one more of these. Now normally when I go in, the software, I allow the software to do a majority of the analysis, but I usually double check behind it anyways, just because that's the way I am. So let's change the minimum dB level in this case. So we can see the noise floor. There's my running speed peaks. They are below 65 dB down, so it's not going to call unbalance. I do have a peak associated with, so that's blade frequency here, and then that's a line frequency, so add them together. So 60 and that, 60, oh, I think that this is actually incorrect. It should be 6 blades. So I just have to change it here, and what's really neat is if I have made a mistake, I can click on that and poof, there it is. So 60 and 90 is 150, so right around 150, there's a peak there. That is a blade frequency. So I just want to make note of that, and then I'll pay attention to that when I look at things like turn-to-turn shortfalls. Again, all the noise down here, there is a heightened pole pass frequency, but that's buried in here. So I normally won't make a call unless I have a definitive pole pass frequency peak showing up past that point. So let's go ahead and let's do the shortcut just for fun, because there we go. Now it says bearing indications detected. So this particular one, so potential bearing fault. Let's click on bearings. This would be a bad cage. We know that, actually do know that these things had bad cages. They're pretty old and hadn't operated in a while. It's oil filled, so there's some rust going on inside there. So everything else looks all right, but I can also confirm that by going into my, going into my high frequency data set up here, which we were going to do anyways. Notice also this is 120 dB down. There's all my noise. Let's get rid of that so that the peaks look more impressive and scary. I do like using the larger screen if I'm trying to impress my friends. So anyways, let's take a look real quick. Unlike the last one, I am not seeing a significant blade frequency. It's very low. It's below 65 dB down, whereas the other one was up here. So I do have that blade frequency here. So let's take a look, and this is the second blade frequency. The second blade frequency is related to what we saw before. That's my running speed sidebands of my line frequency. Let's take a look at interturn shorts. So ignore this one because it's line frequency. I do have one here at about 90 hertz. That's not unusual. And I do have one in closer here, 75 hertz. These, this is actually the running speed, so I'm not going to pay as close attention to that. I do have some definitive peaks now showing up here. So right now I'll call that cavitation. I'm not seeing anything that would say that it's rotor bars, and I'll explain that here in a minute. Let's now take a look at bearing damage. So let's take a bearing. Now we come in here and we take a look. There is a bearing peak there. There is no bearing peak there. So this is most likely the one that's related to the cage. And I don't see other bearing peaks. So that is just a cage frequency then. So it's something we should consider. So the cage starts to come apart, we will have problems. So let's back up again and we'll take a look at static. No static of any significance. Dynamic eccentricity. No dynamic of any significance. Notice they're not covering a bunch of peaks. Stator mechanical. Oh my gosh, here we go again. So for some reason, these two machines that we tested before and after have moving coils. It could be things as simple as the tie downs not being good enough, or the bracing not being good enough inside the stator while it's running. Now this is running at about 75% of load. So yeah, so some movement can be expected. Okay, so let's oh, and we'll come back to this again as soon as we hit the low frequency stuff, because I want to show you one more thing here. Now, I said that could it be rotor bars? Well, I don't see anything indicating rotor bars here, so I would see a regular pattern if it was rotor bars. At worst, maybe casting. Well, no, this is a copper bar, so yeah, it's definitely, it would have to be rotor bars, and this would be in a regular pattern. That is covered under a different presentation. So we've looked at two of these. Let's go ahead and see what a report looks like real quick in EMPATH. So I have this potential bearing. It does note that subsynchronous peaks are detected in DMOD, and the noise floor is below a value that we expected. So let's go ahead and open this up. Now this would put this machine into a database. This will allow me to copy, and this of course does the analysis. So the database allows me to trend. So if I want to go in and do a trend of this particular motor, if I have a whole bunch of tests, it will show each of those peaks as I showed back here in the extras. So Word is a Microsoft product. It tends to take a little bit to pop up. And there she is. So here is our report. So this is it here. It does a quick checklist. It's in Word, so if I don't agree with something, I can change it. I'll often come up here and I'll add some notes up here identifying the machine, and I might put some additional notes down here. There is a notes section for saving stuff, but if I want a particular message for a report, I'll just type it in, and it won't cause anything to go out of order. This is the nameplate data that was put in. These are all the speed calculations. These are all of my other related information. You'll see on the next one I'll have a lot more. And then here's the basics. Now I don't have torque on this one because I didn't get voltage as well. So let's close out of here. So this was an across the line 60 Hertz machine that has bearing issues. Down here you'll see a peak as well. That will show up sometimes if I have pump issues. I'll usually see something around 5 to 15 Hertz right around here. But this is running speed, so that peak may or may not be there. We'll see that again. So let's go ahead, and this time we are going to not randomly select. We're going to take this machine here. As you can see, I've tested it once before. This is a machine I was commissioning. This is the picture of it here, and here's the nameplate as well. So give it a few seconds so you can see it, and that's the pump station for each of these three pumps. So if I come in here and I select this date, now this one's interesting because there was a lot of cavitation, so there's some things that are going on. You'll also notice this is pretty straight. It goes trending kind of down. This has to do with the pumping part of the system. So here's my blade frequency. Let's take a look at the nameplate. So up here you can see I selected VFD, three phases, both current and voltage. This is one is really simple because it's a Baldor. They provide data readily. So it's 46 rotor bars, 60 stator slots. It's an 1800 RPM or 4-pole machine, 600 horsepower, 460 volts versus the higher. Again, this one has 6 blades, pump. This is actually totally enclosed fan cooled. I can change that again at any time. This has to do with continuous monitoring. This because my data collector is set up also for continuously monitoring. So in any case, this is that, and the bearings are 6322s. I had to decipher what was on the nameplate. The bearing database is significant for when I do. Here we go. I have a bunch of manufacturers, and under each manufacturer I have every bearing they make, pretty much. So in this case I'm just going to keep it there. For that, if I put a -1, what it'll do is it will look for non-integer multipliers of running speed. So here we go. That's all set. I'm not doing any of those. This is the motor database. Has 8,400 electric motors of different manufacturers in it. We're not changing anything there. So that is everything having to do with that. So now we come back to this pump. It's on a VFD, and you can see that I'm at about 40 hertz. It's going to select a running speed. Let's let it do the running speed a little bit. And again, what we're going to do is wait for my computer to get around to it. You can see I got double peaks here, by the way, and that's because this was not maintaining constant speed. So if I come in here, I right click and I do running speed and pole pass frequency. Let it select my running speed. Now I can disagree with it. So if I come in here and I say, you know what, I think this is my running speed, I can do that. Okay. It's going to show me some potential issues. So let's go ahead, and I can also do this. I can say, okay, I think this is my pole pass frequency. Then it's going to start playing around with my running speed. There's my bearing indicators again. So in this case, I have bearing indicators, and this one is saying, ooh, bearing. So this one is saying the balls are bad in this, and we've had problems with this. In particular, we've had some discharging going on. The other thing we will note is because I'm taking both voltage and current, I get a torque graph. So this is my running torque for 10 seconds. I can change that to a longer period of time. And this is my actual torque peaks. This is just over 80 hertz, so that would be just around twice line frequency. So I can take a look and see what's going on there. I can also come in and highlight certain things. I don't have a lot going on here, so it's not a big deal. If I swipe back to the left, there we go. It gives me my torque information, also all the stuff that I can track. And now that I've got both voltage and current, this is what's trended in the database. So all of that's trended. Now I've got additional information. I can even change this to horsepower if I want to impress my friends. But in this case, it'll be in kilowatts and everything else. So there's my amps and voltage. This is my actual real power. This is the power factor going on. You notice that looks a little low. So there's some things I can do to see if that is accurate. But we cover that in the full course. And then down here, 27% of load, full nameplate load. This is the estimated efficiency based upon the ORMEL 96, which is Oak Ridge National Labs calculation. These are losses due to impedance unbalance, usually connections and other issues in the system. And then these are the torque, and this is the output power. So basically it's like an inside dynamometer. This is something that's been here for a long time. Other people are trying to figure out how we do it. Calls rotor bar health questionable, and as you can see, there is a slight pole pass frequency. There's most likely casting voids in this. Be perfectly blunt, based on my experience, I would ignore that. The thing I'm more concerned about is the bearings. Now, if I had pump bearing issues, this would say bearing and non-integer or something along those lines. Would be other than potential bearing. So if it says potential bearing, that means it is one of the bearings that you entered. So let's get back to here. So we've set this. We know the running speed is right around 20 hertz, so it'd be about 60. I'm not seeing, and about 20, so I'm not seeing significant peaks. It means I don't have an unbalance or misalignment. These peaks here relate more or less to this peak here. Now this is an impeller peak. So this happens on occasion. This says the blade peak. I usually associate that with a pumping issue. This I sometimes associate with an actual mechanical issue associated with the pump. Then I have some sub-frequencies that are not related to running speed. We'll take a look at that. So let's take a look at our high frequency data set. Let's see what a VFD looks like. Now we took this on the output side, on the motor side of the filters. So look at that noise. Wow. Now I will sometimes see single set of peaks like this. Sometimes I'll see a double hump. We call it the camel. This always occurs with VFDs, may occur partially also whether if the VFD isn't fully tuned. So this being up here is a little unusual. Those peaks are rather high. So let's take a look and see what's going on here. You can see those peaks there, but let's just go ahead and X in and see what happens here. Let's go in even closer just for fun. And this is what the sine waves start to look like. This noise here is what we're analyzing. These are this is the pulse width modulation coming out. You can see kind of a shadow of what looks like a sine wave in the background. But these peaks here are associated with noise. Those are those high peaks, as well as this one here. So let's step back, and step back. There we go. So let's get rid of these now and do a quick look as to what's going on. So first off, we have, just to quickly summarize before we start analyzing anything here, we know we have a bearing issue. It has to do with the balls on the bearings. So, but I'm not seeing anything significant out of my torque, which is good. Let's go ahead and start taking a look at a few things. So we're going to do the higher frequency stuff. So stator mechanical. Looks like now, why do I like having both voltage and current? Well, let's see. Come in here, we've got peaks. They're relatively close to line frequency. They only exist in current. They do not exist in voltage. Therefore, it is motor related. It's probably some noise having to do or movement of the coils. Not unusual, especially in this type of machine. But if I see peaks in both, if the peak in voltage is higher in dB than the current, then it's somewhere outside. And we've got 3 machines on here, so it could be something from the drive, could be something else. In this case, we do not. We have these so that it is definitely associated with the motor. So let's take a quick look at dynamic eccentricity. So let's pop back. Pop back. Let's take a quick look. I often do this much faster, but for demonstration purposes, we're walking through. I don't see anything here. So let's take a look at static eccentricity for fun. Oh, there's a peak there. There's a peak there. So maybe a little bit of orbit. Not a big deal. I'm not looking for anything in particular in that area, and those are right on top of line frequency as well, so not going to be as concerned about it. Okay. So let's go ahead and back out again, because we're going to get in close down here, and just for fun, let's take a look at this thing called inner turn short. Now I'll show you what we are going to do with that. Down here, we're going to see some multipliers. So I have a line frequency, and there's a peak there. No line frequency there. No peak, line frequency peak here, but there is something else going on behind there. So at 80 hertz plus that 20, and I'm seeing it here as well. Okay, so line frequency I ignore. The non-line frequency I necessarily do not. And I really don't see anything, so we're not going to worry about this one. That means that it's relatively well tuned. You have the blade frequency. That's going to be associated with the issues in this pump that we are aware of. So let's take a look at a second one. And this one we're going to go through much quicker. So let's go ahead and see how I take care of these. Again, a lot of noise, running speed, etc., blade speed. There's a peak down here. I don't see the peak up there. Let's go ahead and take a quick peek and see what's going on here. Okay, jumped right into torque. So here we go, and I am going to let it calculate my running speeds. Running speed should end up right around there. If I do not agree with it, I may select a pole pass frequency, such as right here, just for fun. May or may not change that. Oh, running speed changed. Okay, so we have a change in the running speed. Now let's look and see. Okay, And we'll do it again one more time. Okay, it really wants, this is the running speed, so we'll say it's probably the running speed. Now it's telling me current is changing a lot. Now what's kind of neat is when I run this on a standard system, this screen pops up immediately and it does everything automatically that I'm doing manually right now. So let's take a look. We're at 31% load, yada, yada, yada. We got a higher percentage on balance to do that, so I'm going to check connections. I've got relatively low here. Let's see, all this stuff looks about right. It says current imbalance, and there's just a slight shift that way. It's on the output of a VFD. Not going to worry about it. Bearings look okay. Torque. Now I've got some torque at line frequency and twice line frequency. And then I have some other peaks in here, including this 20 hertz one, which is right around my running speed. It's right there, so I'm going to say that chances are that that 20 hertz was my running speed. So let's go ahead and we are going to change this. I do go through this in depth in a class, so let's go ahead now and we will go back. So there's that. My running speed is 19, so that would be at 60. I don't have any side bands there or there. That would indicate something having to do with unbalance. I do have other peaks going on that are subsynchronous. Those will all have to do with the pump, and there's that frequency there. So let's go ahead. Whoop. Let that open, and then we'll close it. Okay. Let's go to my high frequency data set. I haven't looked at this material in a couple of months, so here we go. Those are all the peaks. I have an option here if I really don't want to have, because I'm looking at three phasing, see black, green, and red. They're going to be the same, roughly, the humps and everything else. If I want to make life easier, I can come up here and turn off those frequencies. Ooh, there is one other thing. And I can turn on that one. Okay, so here I have my voltage spectrum. Here, here I have voltage, here I have current, and this one, you'll notice the peaks are different. This is power or kilowatt spectrum. Now, I have to go in here and manually find these in any case, but these are actually not side bands of 60 hertz, but if I go rotor bars times RPM, I will get a single peak. So this looks more like what you would see. This is more like vibration data, except you're looking at the peak down versus the base up. So we're going to go ahead and close this out because this is that's for the advanced class. And let's take a quick look here. So let's start out with stator mechanical. Do I have anything going on? Not really. That looks pretty darn close to line frequency anyways. Let's take dynamic eccentricity for fun. And we'll back out. And we're going to get down in this area here. I like getting in close so I can see it. That does not look like I have much in the way of that. Static, nor any static eccentricity. So let's go ahead and back out. Let's take a look at interturn shorts. Now, neat thing is on VFDs, if I do see things related to interturn shorts, such as this peak here and this peak here, showing up in both voltage and current, I would say that is called winding stress. So I would usually recommend that somebody go back in and do some type of retuning of the drive when you see those types of peaks. Blade frequency out here, there it is. Also coincides with what looks to be a line frequency peak. So we've now taken a look at that. Let's take a look at the bearings. And we'll get in even closer. So here's a bearing peak there. So if my line frequency peak shows up, let's try to return. Yeah, so probably not going to be that then. So this is more than likely going to be bearing issues. Yep, there's bearing peak. That's with line frequency, so ignore that. There's another bearing peak there, and small peak here. So those would be related to what we identified before, which is the ball spin. Now, when we do the class, we're actually going to go through how that's all multiplied out. In this case, I'm just using the automated calculators in the software. I go in depth in exactly what the algorithms are in a full class. So what we have done in this case is analyzed 4 pumps, relatively short time. I'm going to add some time to it while we wait for Word to get around to opening up a report. You notice also here I'm at about 6,000 hertz. Everything falls off of 5,400 hertz. That's pretty common. There we go. So this is my analysis and my report. Again, all the data that we just looked at, all the findings. Because I've got both voltage and current, you can see here on the left, all of that is there, including a power factor variance between phases. And then I've added my torque and my output torque here as well, and everything else up to including current and then voltage spectra. So that's it. I'm going to go ahead and close this stuff out, and if you have any questions, feel free to contact us at info@motordoc.com. The address will be next. That also includes access to the EMPATH system, which we do sell, and we also provide service and technical support for it. Thank you very much.